is the most famous image in the image processing community. And this is basically image data compression. The image on the left has 256 shades of gray. The image on the right only has 8 shades of gray. So the right image is compressed, not because the number of pixels is reduced, but the information in each pixel is smaller. Here's an image segmentation. This is Europe by night, also a very famous image in the segmentation community. So Europe does a great job at selecting 3 things. The sea, which is dark, the land, which is not quite so dark, and then cities, which are light. So you want a computer to do that segmentation for you. So here's a segmentation into 3 segments. This is a particularly good one because you can hardly see So what we did is we developed a new method, which instead of averaging after every sample, we do lots of sampling, in this case. Then we cluster our sample points according to what they're nearest, so all the blue points are closer to Z1 than to the others. And then we average the blue points, and that's our new Z1. We average the red point, and that's our new Z3. And now I see because the blue points are actually test whether it's a Voronoi tessellation, and you can actually test well how close it is to a centroidal Voronoi tessellation. And this was done, and it was found that this is very close to a CVT. Territorial behavior of animals. The male mouth breeder fish, Tilapia mozambica. So this fish lives in ponds and lakes with sandy bottoms, and the male member of the species digs pits in the sand, which the female member then comes and when it's doing its egg business, comes and uses that pit. And what happens is this is done synchronously by all the males in a given and then do a centroidal Voronoi tessellation in RGB or CMY or whatever space color system you're using, and you do a CVT. Then what does the segmentation of an image look like in color space? Well, everything that's in one Voronoi region of a given color, is in one segment, and everything that's in a Voronoi region of the other color is in a different segment, if you have two colors, for example. So if you keep track of where the color in your color space came from, what is the physical location of the different colors, after you do the CVT in color space, you can assign the points in the original physical image to one segment or another, depending whether their color is in one Voronoi region or another. So it's very, once you have a CVT in color space of an image, it's very easy to then segment the image. This is all explained here. So here are some segmentation pictures. Here are fuzzy images. How do you do edge detection then? Well, that's also edge detection is the task of determining the edges of the segments. And this you can do very easily because you can look at any point in the physical picture and look at it, map it to color space, and determine whether its neighboring points are in a different Voronoi region. And if they're in a different Voronoi region, that's the edge of your segment. That point is at the edge of a segment. If the points on one side are in one Voronoi region in color space, and the points on the other side to the left are in a different Voronoi region, then you identify that as an edge. So that's a simple one. Here's a picture of a bone marrow image, and this is the original picture. This is a two segmentation. This is the edges of a two segmentation done by CVT. Over here you see that really there's three different colors. So this is a segmentation into three segments, and this is the edges. And one of the reasons this is done in medical imaging is to identify weird things like tumors and things like that, which usually have some attribute, not necessarily color, but you don't have to do this with color or shades of gray. You can do this with intensity. You can do this with the heat being generated by that particular point in the image. I mean, that particular point that is imaged. So you can do this, which is one way to detect tumors. So there's many ways to do this. And here's the elbowing effect for that picture, which shows that after so it shows that you gain quite a lot in going from 2 to 3 segments. You don't gain so much going from 3 to 4, and then after that you gain very little. So this is very cheap compared to solving PDE. By the way, if you do 2 segments, you've got to solve 1 nonlinear PDE in the PDE type approach to Igman segmentation, which is quite popular. If you want to do a segmentation into 3 segments, you've got to solve 2 coupled nonlinear PDEs. If you want to do it into 10 segments, you've got to do meshless method, supposedly you don't have to do a mesh. You just throw some points down and you're done. Well, most point placement methods require a mesh, at least a background mesh. So CVTs, as I've shown you some pictures, work for general domains. You can do non-uniform and anisotropic point distributions, and if you want to, you can place some of the points on the boundary. And in the probabilistic algorithm, you only need to know if your sample point, if a sample point is inside your domain or outside your domain, which is all often information you can get from the CAD program that generated your boundary. Now this has nothing to do with CVT. This is how you determine the support radii. So suppose we've chosen the K points in domain by CVT or any other methods. So then you define a sphere centered at each point, having a radius hi. You can use rectangles, ellipsoids, bricks, whatever one. And how do you determine the radius of the support region? Well, you want two requirements. The union of the spheres should cover your whole domain. You shouldn't have any gaps. If you look at the support radii of all the points, the union of all the support radii should leave no gaps in your domain, because otherwise you might get into trouble with your solver. And the intersection between two support radii shouldn't be too small or too large. If it's too small, you're going to also get bad answers. And if it's too large, you're going to get an inefficient thing because you're going to get a big bandwidth or lots of non-zeros in your stiffness matrix. So the two algorithms which are somewhat similar that are in use or have been in use is one by Duarte and Oden, and the other one Michael Griebel and Schweitzer. These also, to determine support radii, involve a background mesh, and they don't give